going to look at some practical examples of .NET and ASP.NET security. So we'll be focusing on private key encryption and some of the classes we can use, hashing methods, private key encryption, digital certificates, role-based security, and ASP.NET security. Most of the examples that we'll find can be found at this page, and we will be using ASP.NET to implement the examples, as it's easier to gain access to these examples. So each of the code examples will have an example program with a test, and then we'll look at the actual code behind each of these examples, as we can see on the web page. So we'll be using Visual Studio 2008, and we'll just open up our website initially to gain access to some of the examples that we'll be seeing. And here they are here. Most of them begin with the word security. It just takes a little minute to actually load up. Okay, so let's look at encryption. For this we'll look at both public key encryption and private key encryption, and then look at hashing methods. So basically there's three main types of encryption. The first type is symmetric encryption. With symmetric encryption, both Bob and Alice use the same shared secret key to encrypt and decrypt. So in this case, Bob takes a message, encrypts with one key, sends it, and then Alice then decrypts with the same key that Bob used. Some of the methods we'll see here include RC2, RC4, DES, 3DES, and AES. Public key uses two different keys, and these are specially designed, where Bob can encrypt with one key, and then only the other key, the other special key, can then decrypt it. This is known as a private key, and this is known as a public key. If Bob wants to communicate with Alice, then Bob gets Alice's public key, encrypts it with a public key, and only Alice's private key can decrypt it. So typical techniques that we see here are RSA and DSA. Along with this, there is a one-way hashing method in which it should be difficult to reverse the encryption procedure. So one-way hashing takes a message and then creates a hash signature of it. So typical methods for this are MD5 and SHA. So with private key encryption, we use a secret key to both encrypt and to decrypt. So with this, Bob takes the secret key, encrypts his plain text into ciphertext, sends it over the channel, and hopefully Eve doesn't have that key, and in some way Alice has received the same secret key, and then she can then decrypt it. We use the same standard algorithm on either side. This algorithm is known to Eve, but Eve cannot crack the code as she cannot get the shared key. So some of the methods that we use are either block ciphers. With a block cipher we take our text and then we segment it up into message blocks. Each of these message blocks are of a certain size, such as 128 bits in this case, and then each of the message blocks are then converted into a cipher block and then joined back together again into a cipher block or a cipher stream as it is sent out. The secret key is then added to each of the cipher blocks. Typical methods here include DES, 3DES and AES. Sometimes we need a fast real-time encryption on limited hardware, and with this we will often use a stream cipher such as RC4, and we see this in web encryption within wireless. For this we take our plaintext 1 bit at a time. We take our secret key, add on a random seed, typically known as an initialization vector, and then the method itself creates an infinite key. That key is then exclusive ORed with the input data stream to produce the output. Exclusive OR works with a 0, 0 gives us a 0, a 0, 1, exclusive OR gives us a 1, a 1, 0 gives us a 1, and a 0, 0 gives us a 0. The advantage of exclusive OR is that none of the actual original information is lost when we do the exclusive OR operation. The problem that we have now, though, is that if we have a message and Eve listens to the message, then she can see the cipher stream. And the problem with this is that Eve could play this back sometime in the future, and it would look like a valid message. Even though she cannot find the encryption key, she can then do a playback. She could also copy and paste bits of the message. She could even spend her time analysing the mapping between the ciphertext and the plaintext. Thus, we often add what's called salt into the encryption process, and this stops the same piece of plaintext arriving as the same piece of ciphertext. So this shows an example where we might take some encryption and we create an encrypted block. And if we have the same data, then it will be encrypted into the same encrypted block. What we often do is add salt, and this is typically done with an initialization vector or IV. With this we take the first encryption block, add on an initialization vector, and then we might increment the IV vector on by 1, say, and then use a different encryption process. An example of this is shown here. We take an image, and without salt we can see here, even if we're using the top quality encryption methods such as AES, we can still see the original parts of the original message information in it, because the image itself is split into a number of segments, so the same segments when encrypted are likely to come out with the same cipher block. If we use salt, we can see here that we scramble all of the original data. So some of the methods we use, we started off with DES. DES uses a 56-bit key, and it's fairly easy to crack DES. So to overcome these problems and to keep compatibility, the 3DES method was created. For this we create two keys, two 56-bit keys. We encrypt with the first key, decrypt with the second, and re-encrypt with the same first key. So the key strength is about 112 bits. RC2 was meant to overcome some of the problems with 3DES and uses 64-bit block codes and from 40 bits up. A competition was held for a much more secure and an efficient encryption method, and Raindal or AES was selected. Okay, so let's look at our first example, which is Security 07, and we go back to our Visual Studio project and find 07. It should be here. Okay, so with ASP .NET, we have two main files. We have the ASPX file. We can have a look at the source, and we can see here that that links to this CS file, and this is our namespace underscore default 5. So those are the two main things that we need to see within inside our CS file, and we should find that our main class there is default 5, and this is the name of our CS file. Okay, so if we go back to our design, we can see here that we've created a text box. If we can find the properties here, this one's called TB message, this one's called TB encrypt, this one TB decrypt, and we have a text box here called TB key. And so I've added an encryption button, and we can see the event on the encryption button here. These are all our other events, and we can basically just double click on the encryption button, and we can see this is the method that's actually called. In this case, we create a triple DES crypto service provider, and then what we do is we create our key and we create an initialization vector. So 3DES itself has two main elements, the IV and the key. The initialization vector is made up with, in this case we're not actually varying it, but we can see here that we have 64 bits within inside our initialization vector. Each one of these characters is worth 8 bits, and that then is converted into a byte array. So we normally work on bytes within inside our encryption process. For the other part, we have 24 characters that we create, which equates to 24 bits. So we end up with a key byte array and with an IV byte array. The number of bytes in each array will be, in this case, 192 divided by 8, and in this case 8. So the first thing we do is that we create our crypto transform object, and then we have a memory stream that we're going to encrypt from, and then we create from this a crypto stream. So this takes the memory stream and puts it into a crypto stream. After this, we can then write out our crypto stream into our ciphertext, and we can convert the encrypted stream back into text using the byte to string method that we have down here. And this takes a byte array and converts it back into, it takes a byte array and converts it into a string. Then, to make sure it's working, we can then do the reverse of it, where we can decrypt from our encrypted memory stream back into text, and we should be able to then check the result. So if we now run the program, so this is 3DES, and we have test, we'll create a key, we encrypt, and we get our cipher stream, and then we can see here we get the result back again. So this has been an example of, as we've not added in salt, we should be able to get the same cipher stream for any test. Test doesn't work, so we'll try this one. And it's not quite watch it. Hello, how are you? We'll just check. We have have the right string here. Not quite working yet. MGD. Try again. Maybe you've left this off. Maybe not. Okay, so we end up with our cipher stream decrypted into the original text. Same thing can happen with RC2. With RC2, again, we can create our cipher stream. So we'll go back to our project, and in this case we're looking for security 6. There we are. So for an encrypted, for our encryption program, in this case we have 12 characters, so it's 12 times 8 gives us our key size. And then rather than create the stream, the IV vector, by giving it a value, we'll just create a byte. So in this case it's a 64-bit IV value that we have. And then we can create the key from here. We create our byte array again. Same again, we create our encryptor, create a memory stream. We encrypt the memory stream into a cipher stream within memory with our encryptor and our memory stream, and in this case it's our write mode. We can then write that out into our byte array and then get the encrypted stream to display in text again. Then we should be able to check it to see if it's running okay. And with Visual Studio we can run a local web server. So in this case we need to set the default page to be this one, just to check it locally, and we run it, make sure that everything is okay. Obviously the IV vector will not change, so when we encrypt we will get the same cipher stream each time. Okay, so it's a similar method. In this case we're now going to look at AES encryption. With AES encryption we use 32 bits here, and we use 16 characters for the IV vector. So in this case we're looking for 15, and we just stop this, and then for 15 you can see here that's an encryption, and that's 32 characters. So if we do a quick calculation, it's 32 times 8, because there's 256 bits here. Okay, so we do the same again. We create our key and we create our IV vector and put it into a byte array. We create an encryptor again with the key and our IV vector, create a memory stream, we encrypt the memory stream with our encryptor and then print it out. So it's the same type of methodology for each of the tests, and we'll just have to make sure that we've started the right page here, and that's the previous page. So we want 15, set that as the default page. If we want, we can go back to the website and be able to find the example there. It should run online, and for this it's AES, which gives the strongest encryption that we require, or one of the strongest encryption methods for private key. It's just taking a little time just to speed up. Oh, there we go. And we'll go back to our, there we go. It's finally came up. Test, and we get our decrypted text back again. Okay, so that was written down. So let's now look at public key encryption. With public key encryption, both Bob and Alice create a public and a private key. Then if Bob wants to send a secret message to Alice, Alice in some way sends her public key. Bob then encrypts the message with her public key to get the ciphertext, and then even Bob can't decrypt the ciphertext, and only Alice's private key can then decrypt it back again. Okay, so let's look at an example of hashing of RSA. So we find RSA, which is tip 8, and our Visual Studio. Okay, so in this case we take our text, we then encrypt. It will create a public key and a private key for us, and then we have our encrypted text and our decrypted text. So we'll just have a look at the RSA method. So again, we create our crypto service provider for RSA, and then we from the RSA, this will create two keys, and then we can export the private key into here, and we can export the public key into this variable here. This will then show the two encrypted keys. We then import them, the public key, because it's the public key we need to encrypt. We can then encrypt the message, and then we can then decrypt it by taking by only loading the private key now, and taking the encrypted data and then decrypting it, and we check the result. So what you'll find is that this example will not run on the website, because many ISPs ban the generation of RSA keys because of a security problem, a security risk. So what we'll do is we'll set that as the start page, and then we'll run it, and we should be able to generate our public and private key. We use our public key to encrypt. So this is what a public key looks like. This is the private key. We use the public key to encrypt to get this text. One thing to notice is that as this is a block cipher, it's working on a large amount of ciphertext, and then the private key is then used to decrypt this to get the original answer again. Hopefully every time we run it, we'll get a different set of encryption keys. Each of them work. method, encryption method, is one-way encryption or hashing. With this, we take some text, we put it through our hashing algorithm, and then we get some sort of hash signature. It shouldn't be possible, or it isn't an easy task to be able to reverse that back into the original text. So for example, we might have some text here, put it through the hash, and we get a hash value. Eve shouldn't be able to guess what the original text actually was. Typical methods that we use is MD4, MD5 and SHA1. So for example, NT, XP and Vista use an NT hash using MD4 to store the password. Cisco devices also save a hash, an MD5 encoded equivalent of the password. Unfortunately, it suffers from a dictionary attack. In this way, Eve can actually go through all the possible text values and generate a hash table, hash equivalent from these values. Eve then looks up the table, finds the hash value, and then can reverse it back into the original text. Another problem is that we might have a collision where it is possible for different text to produce the same hash signature, and it's been shown that MD5 can produce what's called a collision within less than a minute. SHA1 is better with a time of 18 hours. Okay, so let's look at an example of generating MD5 in SHA1 and the other methods. So we look at security example 3 in this case. And we just stop this from running, and we go to number 3 and look at design. So this is the input text, and then we have a look at our code here. So what we do is we create a crypto service provider again. It's fairly easy in this case. We then convert our text into a byte array. We then take that byte array, then compute the MD5 hash from that byte array. This produces an output byte array. We can then use a byte to string method, which I've created here, to convert it from a byte array, 1 byte is 8 bits, back into a text string for us to display. So in this case we can then run, and we're running the wrong one. Just make sure we get the right one. We want to start number 3. Set up startup. We run that, and then we should be able to generate a hash signature. If we take the word hello, every time we run it, we should be able to get the same hash signature. We change one letter of it, and we should be able to get completely different hash signatures. Okay, so that was our original code. The problem, as we've seen with hash signatures, is that they are often, we can use a dictionary attack. One way around this is to add salt to it, so that we can have a range of hash signatures for the same original ciphertext, and it becomes more difficult for Eve to try and guess the original text. Okay, so if we look at example 3b, we should be able to see an example here of this. Stop there and go to 3b. In this case I've added in 4 strings as passwords to increase the number of possible hash signatures for a single instance of some text. So we just set that up to be the startup, and we just run it, and what we should see now is that the number of signatures created should increase. So it's used the word text as the salt. Let's use the word text again, should give us the same hash signature. Let's use Bill, and we can see a different hash here. There's a different one again using Fred. So the more salt elements that we use, the greater the values of the hash signature will be for a single instance. Okay, so it's a very similar code, but in this case we add in some salt, and then we use that as part of the hashing function. The last method with inside hashing is HMAC. With HMAC we provide both authentication and validity of a message. So in this case Bob sends the word hello, takes a HMAC signature of it, and with HMAC we have a shared private key that both Bob and Alice know. Then that signature is then sent over. At the other end, Alice receives this. She does her own HMAC with the same shared private key, and if the hash signatures are the same, then she validates the message, and she also validates that it was the correct shared key that created the message. Okay, so example 1 will give us an HMAC example. So we'll just set this one up to be the startup, and just load it up. So in this case we've got a message, we have a key, and we generate HMAC from it. It's a similar way as before, but in this case we get a key byte, and when we create our original hash objects, we use the key byte to create them. So if we just try this, and a weakness of some of these methods is that we're obviously using strings, well-known strings, for our keys, which can be easily guessed. But it's useful to use them as a test. Hopefully, if we use this one with hello, and then we should get the same HMAC produced. Nope. Obviously slipped up. Oh, sorry, that's the SHA one that I've created then. So that has worked perfectly. So let's look at how we can use digital certificates within ASP.NET and .NET. So with digital certificates, get round the problem is, how does Bob get his public key to Alice? Also, how does Alice authenticate herself to Bob? With this, digital certificates are often used to send public keys, and also to identify identity. So with a certificate, we get the basic details of the certificate, especially who it's issued to and who it was issued by and when it's valid. The key thing we see is the public key. In this case we have a 2048-bit RSA key. We often don't see the private key if it's a distributable certificate. This is the key here. We should see a thumbprint to make sure the certificate hasn't been changed, and especially the issuer. If we just try and have a look at here's an example certificate that we might have, some details and serial number, and we should be able to see the public key here, and we see there that SHA is used as a thumbprint. Okay, so we get two types of certificates. One is when we buy a certificate or are issued it, then we get this type of certificate that has both a public and a private key on it. When we export our certificate, we will again get this type of certificate which only has the public key on it. So the public key format looks, if we've just bought a certificate, we might get an email and it might have this body of text, and it's this body of text that we can use to import into our certificate. This shows an example of how to import our certificate into our storage. So an example that we might see, we can copy that to file and export into a base64 format. It tells us what do we want to export, and that's it. And then let's see if we can get to Vector. Okay, so we have our format here. Okay, and this is how we tend to use our certificate. If Bob wants to send Alice an encrypted message, she can send her digital certificate. Bob will then take her public key off that and then encrypt it, and then Alice can use probably her other certificate, which is the public and private key, and then decrypt that message. We can also use it to provide identity, in that Bob actually encrypts a hash method with his private key. Then he forwards his digital certificate to the other side. Then Alice decrypts the message with a private key. She ends up with a hash signature. She can then use Bob's public key to decrypt that hash, and if she gets the same hash signature as the one that was taken from Bob's certificate, then she knows it was Bob that had sent the original message. Okay, so let's look at the code, and this is security example 10. Just stop here, and what we'll do is we'll run it locally and then see how it runs on the website. So this reads in some details from the server, and then we can open up the text inside the certificate. So we'll just try and run this now. Example 10. We can view that certificate, and just in some text. So that's what the certificate actually looks like. We can import that one if we want. If we actually load it up from the server, we can see here there's some of the details, basic text, the algorithm used, the issuer, and so on. Okay, so let's look at some role-based security. As we'll see, role-based security allows us to be able to easily lock down our applications. So with this, what we tend to do is that we tend to identify users and then link these to their role. So in this case, Bob has an administrator role. He might also have another role, such as part of engineering, say, and the rights that he gets depends on his role and not necessarily from his ID. And then we can have roles such as guests, which will have limited rights on the system. So when we deal with a web-based application, the main types of authentication that we can then get based on a role-based authentication are built-in windows, where we can get the local Windows registry to authenticate a user. We can get passport-based authentication, such as from Windows Live Passport. Form-based, where we can authenticate a user by them entering a username and password into a form, and then integrated IIS authentication. So too often our applications themselves do not take role into account, and that they often sit alone. As much as possible, we need to understand the role and the identification of the user to enhance the overall security. So the main interface that we have is called iPrincipal, and from this we get the Windows Principal class, and this allows us to be able to create an ID for a user. So in this case we have Windows Identity, and we use the getCurrent method, getCurrent, and this will give us our ID. We can then define what the identity is, the name, how it's been authenticated, and then we can actually define whether it is a built-in role, such as an administrator. So the main types of tests that we can have is it an anonymous user? Have they been authenticated? Are they a guest? Are they a system and system account, and so on? And then some of the built-in roles that we have are administrator, guest, power user, and so on. So if we have a little look at an example, and our main example here is integrated into an ASP.NET page, and it's security 11. So we'll just go back to Visual Studio and find this one. It's in here. So if we find security 12, we just set that up as the default page, just to test. Let's check. Security 12, security 11. Okay, so in this case we'll enter some basic details. We'll get the current identity. Because it's running from the web server, it's likely to have a delegated role. So we'll just set this one up to be the default starting page, and we have a look at the code that we have behind it. So we get the Windows identity, get the name, authentication type, and then we can then use this to decide is the user an administrator, So as we said, some of the roles that we have are guest, power user, and so on. If it's an administrator, then it will show you're an administrator. If not, then it will say you're not an administrator. So we'll run this example. And then what we should see is the role that we have actually on the web server. So we can do the same for any Windows program. It can run in the same way. Just takes a little minute to load up first time. Should get there eventually. Okay, so we can show the role, and we can see here, here's my ID, this is my login. It is coming from the local Windows identity, and it says that I'm an administrator. So Dotnet has a strong and integrated security model which is scalable across corporate infrastructure. One of the problems that we have with our system components is called DLL hell. With this, new components can be saved in a place that has existing DLLs, and thus a previously loaded DLL might look for a certain version, a previously loaded application might look for a certain version of a DLL. If a new one comes along, then it can overwrite the existing one, and it can cause our existing applications to crash. Dotnet tries to overcome this by giving each of our DLLs and our components and assemblies a unique name. This is defined as a strong name and uses a cryptography function and digital signatures to be able to uniquely define our assemblies, and it overcomes DLL hell. We can see here an example of our global assembly cache, and we can see that there can be multiple versions of an assembly inside our global assembly cache. And then if we have the same version, then we can have different signatures for each of the assemblies. To generate the strong name, we need what's called an SNK file, and this holds a public and a private key, and it is up to these keys to be able to sign the assembly to give it a unique name. In this case we have a text name, a version number, a public key, and a digital signature. To generate our public key pair, we use the SN utility -k, and we generate an SNK file. Once we have that, we can then add this into our assembly and sign it. So in this case we see an example here of an assembly, and it has a certain public key token and a version number. When we integrate this into our components, we then add our SNK file. So if we just try and find an example of this from here, see. Okay, so in here we should find that we can add in our SNK file into our assembly key file. Okay, before we look at the .NET security model, we'll look at an example of how we can register a DLL into the cache. Okay, so here's an example, and we'll just build that, and then this should create a DLL for us. Okay, so that's succeeded. Just a very simple DLL. It has two methods, multiply and divide, in there. And now what we'll do is that we'll register this into the global assembly cache. So the DLL we have is here. And then we can use the global assembly cache util to register the DLL into the global assembly cache, and then we should be able to find it in there. So once it's in there, then all the applications within inside the machine can actually get access to it. Okay, and have a look at the .NET 2 global assembly cache, and it should be in here, and we should be able to identify the unique name for it because we signed it with a strong name. So if we just look down, we should be able to find it in here somewhere under my math. And here it is here. So we can see here it has a certain version number that we've actually given it, and here is the public key token here, and the version and the public key token along with the assembly name should be able to identify the assembly correctly. So let's have a look at the .NET security model. So it is built around a hierarchical infrastructure where we have a global enterprise security policy, then we have a machine policy, and then eventually we have one built around the user. So with this we have XML files which define each of these. So for the security configuration, we have enterprise security.config, and then at the machine level we have security.config, and then at the user level we have a more refined security level. Along with this we have web.config for web applications and app.config for Windows versions. And this allows us to customize the security of either web or Windows applications. So the user policy is so the .NET security model is built around enterprise, machine, and then user. So the highest level is enterprise, the next level down is machine, and then the final is user. The main .NET configuration policies are typically saved within inside the framework folders. So in this case we can have a little look. So this is an example for .NET 2.0. So we can see here there are a number of config files. So we can see in here enterprise, machine, and security. There's also a web.config in here. We'll see how that's used later. If we look at the enterprise one, then within inside here we can see a number of XML settings that we have for .NET. So the machine tends to store multiple versions just in case there is a problem with one, so that the system can backtrack to a previous one. The main focus for this part of the presentation is on the web.config file, and as we'll see, this is an important file for defining the security levels for our web-based applications. For this we have a special file called web.config, and this has an XML format and defines many of the security features for our web pages. The web.config will then control all those web pages within inside a certain folder. Any subfolders, the web.config within those folders will actually define the security for those folders. So obviously we don't want users to be able to view this file, so when they do try to view it, it should give some form of error. If we have a look on our own web server here, and inetpub www-root, and we should find that we have a web.config file here. But then when we actually try to access this file, then hopefully we should get some form of error. There are a number of tags that we see inside the web.config. These include authentication. This defines how we're going to authenticate to the user with a form or with a Windows database, user database. Authorization is who we authorize, and other things like compilation. We can have a debug flag to show debug information or not. So we can have authentication mode of Windows, and that will check the local user database to see if they have a valid account, or we can use forms where we can redirect the user to a form to log in to. It's also possible to use a password to get a single logon and to profile from member sites, and of course we can get an authentication of none. So let's try a simple example. So in this case we'll take a default page such as this one. Okay, so what we'll do is that we'll set that as the home page, and then we'll go to our web.config, and we can see here the authentication is set. So it helps us to write these tags. We'll say none initially. So now we should be able to go straight to that page and access any other page within inside this local website. Just takes a little minute to start up, and we can see here this went straight to the page. It's just initializing, but it should load up. And what we'll do next is to modify the web.config file so that the user cannot get straight into this page. Just takes a little minute. There we go. So everything's worked fine there. So now what we'll do is that we'll make sure we'll come back onto the Windows authentication later, but we'll uncomment this out. And we'll take this one, put it down there, and we'll take this one and put it there. Okay, so now we have authentication of forms. We do not allow any guest users. If we go back to our presentation, so with our authorization we can deny certain users or allow or deny certain roles. If we have the question mark, it's the anonymous user, and the star identifies everyone. So in this case we will not allow anonymous users in, so every user should go into the form. So the form that we're loading up is login.aspx, protects all the files. So then we'll just have a look at that. Okay, so we have our code here. We'll just look to see what we have. So this will take the username as the username from the form, and also the user password, and feed it into the password. So only when the two actually match will it be successful. Okay, so now what we'll do is we'll just stop debugging. We'll now run the file. Hopefully the web.config file has been saved. So now what should happen is that we shouldn't be able to get access to any of those files, and we should get a login. So it's went to them. If we try the wrong username and password, shouldn't allow us in. Now what we'll do is we'll enter Fred, and the password for Fred is pass1, and that should allow us in. Okay, so we should be able to, once we've signed in once, we should be able to access any other of our files. So we can see here the web.config file has allowed us to get access to define the usernames and passwords. If we made this a star, then no one would allow in, because it says deny all. If we made it just for Fred, then we could deny just Fred. So there are various other tags that we can actually use with inside here, and we can define an impersonate. If the impersonate is set as true and the authentication is for Windows, then our Windows identity gives, and the other HTTP identities give us the domain and the username. If we say the impersonate is false, then we can see here that the Windows identity gives the ASP.NET name, which is the name of the user who is running the ASP.NET machine. So we can see in this case, when it was set to true, then that user is being impersonated by the user who has logged in. So let's look at the infrastructure that ASP.NET provides. So at the start we have a client, and the client will then connect into a web server. The web server itself will be running as an IIS service, which is built upon on ASP.NET. Then we can have various ways that it can integrate with a middleware service. It can either be built around web services, or if speed is required, then it is often built around .NET remoting, which allows the call to DLLs. Or for a robust enterprise environment, it might also involve the integration of COM+ components. Then we can have our back-end database server. Along with this, we have some secure communications using SSL or IPsec to make sure the complete conversation is secure. So we have authentication of the clients of the applications. Then we have authorizations, and that's the access controls that are required for the clients. And then we have secure communications. So the two main methods for integrating our middleware is to use .NET remoting. With .NET remoting we have DLLs distributed around our system. We have some sort of listener which is waiting for calls, and then in .NET we have a local proxy where the client communicates with the proxy, and the proxy then communicates with the remote components. For a web services based system this tends to be slower but is more compatible on a range of systems. Again, we have a local proxy and the client communicates with that proxy, which then communicates with the web services. We can also have a COM+ type environment. In this case, this is an example of a COM+ component or a service component, and this is added in as a COM+ component to our system. So at the first level we have our IIS security. So one of the advantages of a web-based approach than a normal Windows type infrastructure is that we get the IIS security built into it. So the levels that we can have for this is anonymous authentication, basic, digest, integrated, or certificates. And with the authorization we can get normal NTFS permissions or IP restrictions. So if we have a look at our web server, settings, control panel, and administrative tools, and then IIS. This takes a little minute to start up. Okay, so this is the Vista version. So we can see here that we have our web server running, and we can stop it if we want. It's running for both port 80 and port 443 for secure communications. So with inside our IIS we can have a look, and we can see here that at the present time we have anonymous authentication. So if we go back to our Visual Studio application, here, and we'll make it Windows authentication. We'll just comment this right out. To them. Okay, so now if we have Windows, let me just save that. Now when we run it, the IIS has defined anonymous login, so it shouldn't ask us for any logins and should go straight to the page. It just takes a little minute to start up. Obviously it would be much faster if it was running from the local web server, and it should get there eventually. There we go. Okay, so now what we'll do is we'll actually go to the proper server. So we look at our web.config file, and we'll find our authorization. Okay. Just run the web server. Okay, so everything's worked fine there. So now what we'll do is that, so it's purely using Windows to authenticate. And if we look back at the config of IIS, then we had anonymous enabled. So we'll disable it. And now what will happen is that we'll get basic authentication. So now we'll disable, just make sure that we have that set. So we've set it for basic authentication. And we have Windows here. So now when we access our web server, we see here that we get a login. So if we get that incorrect, if we don't have a user called this, then we should be able to get access to our page. And now what I'll do is I'll log in with a valid local username, and it allows us to get in. So you can see what's happened there, and that because we set this to be basic, then it will use the local Windows database to authenticate the user. The only problem with this is that the username and password is set in a plain text format using base64. If we use digest, it makes a basic hash of this. Okay, so we've seen there that we can actually apply the local database to provide the authentication. So anonymous was no authentication, basic is in base64, digest is better because it has a hash signature, integrated allows us to integrate with a Kerberos type infrastructure, and certificates uses a digital certificate infrastructure. Okay, so we've seen that when we set up, we enabled the anonymous authentication and it allowed us in without any usernames and passwords. Then we changed it to basic and we needed a valid local username and password. With our NTFS permissions for the www root folder and other folders, we can actually set the permissions locally. Then we can set IP restrictions on the actual connections that we get. Okay, so we can actually add them here. So let's say that we want to allow all of these addresses. And that is defined in our IP restriction. So in this case we can lock down our website to only machines that we trust. At the next layer we see enterprise services, and with this we have authentication using the RPC protocol and the authorization using COM+ roles and also NTFS permissions. Then for SQL we can have Windows authentication or SQL authentication, and with the authorization logins, object permissions, database roles, user roles and application roles. What we've seen before was the impersonate equal to true, and with this we can access a local resource by impersonating a user. With delegation we are allowed one hop to access a remote resource.